This video looks more closely at sampling distributions. Sampling distributions are sample size specific. They're also theoretical. When doing research, we draw one sample, then calculate a sample statistic. This statistic falls somewhere on the sampling distribution, the distribution of all possible values for the statistic. When the statistic is a mean, this distribution is called the sampling distribution of the mean. Suppose we're interested in determining mean resting heart rate for UB graduate students in the health sciences. The population consists of all 200 such students, from which we draw a sample, measure each subject's heart rate, and calculate the sample mean. These dots represent the population from which we draw our sample. Let's choose a sample size of 30. The red dots represent one possible sample from this population. Here's another possible sample, and another. If we do this repeatedly, calculating x bar for each sample, and then plot all these means, we will have produced the sampling distribution of the mean. We only draw one sample, but we know that our sample mean falls somewhere on the sampling distribution. We also can determine what the sampling distribution looks like without having to draw a lot of samples. Suppose that we know that the mean for the entire population is 72 beats per minute, and that the standard deviation is 5.5. These are population parameters, and we almost never know these values. We'll also assume that the population distribution of resting heart rate is normal in shape. We randomly sample 30 graduate students from the population, measure their resting heart rate, and then calculate the sample mean. If we had heart rate values for all members of the population, its distribution might look like this. It's normal, so we know that if we standardize it, we can find the probability between any two values using the formula for z. For example, we could determine the probability that a member of the population had a resting heart rate between 72 and 75 beats per minute, or below 68. We are familiar with this distribution, but unfortunately, we're not interested in it. We have a value for x bar, so we need to compare it to a distribution of x bars. Comparing x bar to a distribution of x would be like comparing apples to oranges. We need to compare apples to apples. So what does the distribution look like? It has four important properties. Its mean, mu x bar, is equal to the population mean, and its standard deviation, sigma x bar, is equal to the population standard deviation divided by the square root of n. The standard deviation for a sampling distribution is called the standard error. Mu x bar and sigma x bar are parameters of the sampling distribution, just as mu and sigma are parameters of the population distribution of scores. When the population distribution is normal, the sampling distribution will also be normal. The last property has to do with the shape of the distribution. As the sample size increases, the sampling distribution of the mean becomes more and more normal in shape, so that if n is large enough, at least 30, x bar follows an approximately normal distribution, no matter what the shape of the population distribution. This is referred to as the central limit theorem, and it's actually pretty fantastic because it means that we don't even have to know the shape of the population distribution in order to know that the sampling distribution is normal. For example, none of these distributions are normal. But if our sample size is at least 30, the sampling distribution of the mean for samples drawn from these populations will be normal. These properties are important because they allow us to determine probabilities for x bar. Going back to our example, we drew a random sample from the population, measured resting heart rate for each subject, and then calculated a sample mean, which we can now locate on the sampling distribution. Let's take a look at this distribution. We know that it's normal because the population distribution of scores is normal, and because the sample size is large. Its mean is equal to the population mean, and its standard deviation is equal to 1. Suppose we want to know the probability of drawing a random sample with a mean resting heart rate between 70 and 72 beats per minute. We can sketch out the area and then convert 70 to z. This z-score will tell us how far away from the mean of the distribution this value is in standard deviation units. This formula looks a little different than before because the parameters of the distribution are different. When we plug in the sample mean and the parameters of the sampling distribution, we get a z-value of -2. Looking up the area between the mean and a z-value of +2, we find the probability of getting a mean resting heart rate between 70 and 72 beats per minute is 0.4772. Here is a direct comparison of the population distribution of scores and the sampling distribution of the mean. Our focus is always on the sampling distribution. Its mean is equal to the population mean, but the standard error is much smaller than the standard deviation in the population distribution, which is why the sampling distribution is much narrower. The normal distribution can also be used with proportions when the sample size is large enough. Using the same population, suppose we want to know whether or not students are working while in school. The parameter of interest is the proportion who are working, and let's assume that 65% of all students are working, that is, that the population proportion is 0.65. We collect data from one sample and calculate the sample proportion p-hat, which is our sample statistic. The sampling distribution is the distribution of all possible values for p-hat. Its mean, mu p-hat, is equal to p, the population proportion who have jobs. And the standard error is equal to the square root of p times q over n, where q is the population proportion who do not have jobs. N times p-hat and n times q-hat must both be at least 5 in order to use the normal distribution as an approximation of the binomial distribution. P is 0.65, so q is 0.35. The mean of the distribution is 0.65, and the standard error is approximately 0.087. We might want to know how likely it would be to draw a sample and find that the proportion who work is at least 0.8. This is p-hat, so q-hat is 0.2. Is the sample large enough? The rule of 5 has been satisfied, so we can use the normal distribution. We want to know the likelihood of getting a value for p-hat of at least 0.8, which is the area above p-hat. The formula for z is again a bit different because the parameters of the distribution are different. We get a z-value of 1.72 and use the table to find the area above z, which is 0.0427. So the probability of getting a sample proportion of at least 0.8 is 0.0427. Sample statistics are random variables and have probability distributions, called sampling distributions. Sampling distributions are the cornerstone of inferential statistics. The next topics will build on this foundation to test hypotheses involving means and proportions.